Yeah, so as I said, I'm going to give so there's 3 things I want to make you understand or have more insights into. So basically, what is streaming? Why is this interesting? Then what's the technological landscape in streaming? So what are the technologies there? Flink is one of the technologies, but there's many different other technologies that are also interesting. And then I want to try and explain why I think that Apache Flink is special and interesting. So let's dive right in. This is a stream. So the idea behind this is that there's water continuously flowing, while this is not a stream. That's a lake or a pond or what you might have. And there the idea is that the water or the data is there and sitting there and it's not changing, basically. So the basic differentiation is in streaming you have potentially infinite data, and the other case is that you have finite data, and this is what we usually call batch processing, because you have, before you do the computation, you have all the data, you can process it in one batch, and then you have your result. While in streaming, you have continuously arriving data, and you need to react to this and make decisions on this. And in some cases, if you're doing stream processing, it can feel like this dog. I really like this picture. Basically, the water is the arriving data, and the dog is really just, he's going crazy about all the data. So in a nutshell, just to, so we are on the same page, infinite stream of incoming data. You also want to make up-to-date decisions based on this incoming data. But this is basically comes from that. You don't want to wait for your nightly batch job. So what people used to do is you collect the data that would come in over the day, store it in some data warehouse or in some distributed file system, and then you would have a nightly batch job that derives some result from this data, and then you can react based on this. But with this, basically, you have you always are 1 day late, basically, in reacting to data when you might want to react the second that some interesting development comes up that you have in the data. So just some examples where you have stream processing use cases. So for example, web shops. In a web shop, you have users interacting with the website. They are looking at items. They're putting items in the shopping basket. They're buying. They're interacting in all kinds of ways. And all the web shops, they always track all the user interactions. And this is basically your stream of incoming data. And ideally, you want to make some decisions based on this incoming data. So you could, for example, offer some special services to users if you notice that something might be going on, or if you might have your tracking or your delivery system in also added to the stream so that you can track whether parcels are shipped on time and arrive on time, so that you can, if something is going wrong, you can react to this, basically. Another field where this is very interesting is financial transactions. So you have all these financial transactions flying around the world. You have people moving or being in different countries, using credit cards. You have people stealing credit card data, using credit cards in different countries. And you have all the interactions with credit cards or with bank accounts and so on. They create events that arrive as a stream. And it would make sense to analyze this stream and react based on this, so that you can, for example, in the second where a fraudulent transaction occurs based on stolen credit card data, you can react to this and, for example, block the transaction. One interesting case is mobile carriers. So just before we had the talk from Telefonica about how they are dealing with data that occurs in mobile phone carriers. So you have all this data about text messages being sent, calls accepted, canceled, and so on. You have the location data. And based on all this data, you can also learn things and do clever decisions in real time if you have a stream processing system. Then another thing that people don't always think of, so that's the Angry Bird. Lately, these online games have become very popular, And mostly the model in these is that the game is mostly free, but you can buy gimmicks in the game to help you win in the game and so on. And what companies try to do, this is maybe a bit on the dark side, but that's the reality, what's happening. They analyze how people are doing in the levels, how they're progressing. They might realize when someone is frustrated, and then in the right moment, because they analyzed all this streaming data, they can offer him some special thing that would make it easier for him to win the level. And then the user buys this, advances in the level, and then he's happy and keeps on playing. So this is the reality, this is what's happening. And very generically, the Internet of Things is a buzzword nowadays, but it's true that a lot of devices and things will be connected to the internet, and they will send data. So there's phones, you can have the smart microwave, the smart scale, your car, your bike, plant sensors, and all of this data needs to be, or if you want to make decisions based on this data, it needs to be collected somewhere, and it's continuously arriving, and you feel just like this dog drinking from the water hose. So what do all of these cases have in common? So I'm simplifying quite a bit here, but in the end, what they have in common is that they count events or things occurring over certain periods of time. So the problem in streaming is that because of this infinite data, you can't really wait for the data to be finished and then say, I saw 5 user interactions, because it's infinite. So what you have to do is you count things over periods of time. So you count, for example, for 1 hour or 1 day or other things. And I'm saying counting here, but of course the cases are sometimes way more complex. But in the end, it boils down to storing things and counting them. So now let's see what a parallel streaming architecture might look like. And we'll see in a minute why I'm saying parallel here. So you might be thinking, I can just have my one computer, it's sitting on my desktop, or might have a laptop. And here, for example, I have tweets coming in. So Twitter is a huge source of events. So all the tweets that are being written or tweeted, and all when users look at tweets, that's impressions. And all these interactions on Twitter, they create also events that you might want to analyze. So you might think, yeah, I do this with my computer. But then, remember this guy? The data that is arriving is way too big to be processed on just one machine. So what you ideally want to do is parallel stream processing. So you have, let's say you have a cluster of machines sitting around. So let's say 3 servers, and there's tweets coming in. And then you would have a system that cleverly distributes the work to these machines so that you can produce results. And that's basically what a parallel stream processing architecture is. And so we're going to look into the components of such a parallel stream processing architecture. On the left, there's all kinds of devices that can be sources of events, of things happening. And then mostly you have, or basically you have 2 components in your streaming architecture. There's a log component, which should ideally also be parallel or distributed. So you have a cluster of PCs that are used for storing the incoming data in a log file, so that other components can read from this log file and do analyses. And for this, you would have the stream processor. That's the 2 basic components. And what's happened recently is there's Apache Kafka, which is a distributed log that originally was developed at LinkedIn, because they also have a lot of events coming up all the time, and they needed to have a good solution for this. So the Kafka is a distributed log implementation. And for parallel stream processors, there's a bunch of different things. So there is Apache Storm, which was originally developed at Twitter for doing parallel stream processing. There's Apache Samza, which was originally developed also at LinkedIn. there's Spark streaming, Spark was originally developed at UC Berkeley, but I guess some people already know it. But now it's developed by Databricks. And there's, of course, Apache Flink, which this talk is about. So I'll come to some interesting stuff later about this. So, of course, what I would suggest is that the parallel streaming architecture looks like this. You have your Kafka, and you have your Flink for processing. So what does Flink give to the user? Or what, if you use Flink, what would you do? So there's, Flink provides an API that you can use to write programs. And then Flink takes care of taking such a program and making it execute on a cluster of machines. So basically, you write in the nice API, Flink takes care of parallelizing it and making sure that everything runs together smoothly. So let's look at an example. This is the only time I'm showing code here, but it's a very simple example of how we would do a counting job in Flink. So there's, initially we're defining a source to read from Kafka. Then what we're doing is we have the source and we say, I want to key the data by country. So what this says is if I do some counting or if I do some distribution of the data, I want to do it by country. And then we say, give me a time window of 60 minutes. So windows, we call these periods of time that you have in stream processing if you want to do aggregations. And then I say, I want to specify my count function to count stuff in this window. That's a very simple example of the Flink API. Then there's, for executing this on the cluster, there's several steps that such a program has to go through. So up here, we have our little API program. What Flink then does from this is it creates what we call a job graph from this program. And the job graph is, it's essentially, it's a graph where we have different operations. So there would be, and the connections between operations. So for this simple example that we wrote in Java, there would be a Kafka source. This would be connected to a count operator. And then I omitted this, but this then would be maybe again written to a Kafka sink so that other programs can consume this data. Now we have to make a quick detour. So if you have a Flink cluster running, what you would have is normally you have a master node in your cluster. This would take care of orchestrating the worker nodes. So the worker nodes are the actual servers that sit in your cluster and do the processing. And the master node is what takes a Flink program that you write in the API, transforms this in a job graph, and sends it to the workers so that they can parallelly execute this. So this is basically the whole life cycle, if you will, of a Flink program. So you write it in the API. This gets transformed into a job graph of these operators so that we can work with this in parallel execution. This is sent to the master node. The master node then parallelizes this job graph into basically based on how many workers you want to allocate to this job, for example, based on how you estimate that what the data will look like. If you have very high amount of data, you would want more workers. If you have less data, maybe one worker is enough. But the master makes sure that this is parallelized and then sends it to the workers, and then they execute it. And this is just, this is a screenshot from when you actually have a Flink cluster running. So there you would see your operators. So there's a source and there's an aggregation. And then in this dashboard, what we call it, you can drill down into the operations and look how much data is being processed, what's the health of these, many other different monitoring things. So now that you know about the basics of why we want to do stream processing, why we want to do it in parallel, now I want to show some of the interesting features of Flink that I think are very cool. And just a disclaimer, some of this stuff is in Flink right now, in the current version that you can use. Some of it will probably make it into the next release. And I also want to highlight this, that we, or I, so at our company Data Artisans, we don't really control the Flink roadmap, but the community does. We're just also developers for Apache Flink, and we collaborate on the community with other people. So that's just my view of how things will probably develop. So let's, for all the examples I'm going to show you, we are taking this basic streaming pipeline as our job to highlight some of the features that are interesting. So again, we have our Kafka source, we have a count operator that counts user interactions per 1 hour windows, and then we write it to Kafka again. Now, before we can understand the next thing, we have to do a little interlude about stateful stream processing and stateless stream processing. So let's imagine we have our operator sitting here. Then we have some data coming in. So this would be a tweet that says #hello Mo. And now we want to know what this operator can do or what it can look at to produce some result. And the difference, or the two things that it can be, the operator, it can either be stateful or stateless. And based on this, it can do different things. So if it's a stateless operator, here we have a chow operator. This means that this operator can only look at the current input event that it is processing. And it doesn't know anything about the history, about other events that it has processed before, about other events that other operators process, nothing. It can only look at this one element. And then based on this, it can produce some result. So the chow operator, it would only look at the text and replace every mention of #hello with #chow, which it can do without knowing anything about other stuff that is going on in the cluster in the processing. So it produces this tweet #chow mo. Now, on the other hand, there's stateful operators, like this count operator. And the difference to stateless operators is that a stateful operator can keep track of things that have happened before. So it doesn't just see the current element, but it can, for example, count the elements that contain Mo that it has seen so far. And then based on this tweet, #hello Mo, it can know that it has seen the name Mo 5 times or 4 times already, and then it can say, Mo was mentioned 5 times now. That's what a stateful operator can do. And there's use cases for both. So for stateless streaming programs or streaming operators, they are mostly used for data ingestion, where you have, for example, data coming from different sources, and you want to put them into a common format, for example, normalize timestamps and this kind of thing. Data cleansing, where you have to bring it into a common format. And for stateful operations, these are these aggregations, basically counting things. There's an interesting thing, it's called complex event processing, or CEP. This is not new, this has existed for quite a while, but now with Flink we're also doing it in parallel. And what this allows you to do is to specify some patterns that you want to observe in the data and then react based on this. So you might want to specify a pattern that says, if I have seen Mo 5 times, then I want to send this message and go to a different state. And if I then see a tweet mentioning Mo again, I want to send another message. So in there you would have state machines that react to the data arriving and change the internal state. And this is, of course, also stateful. And then there's machine learning models. So you might train some model on the incoming streaming data and then do decisions based on the model that you learn on the data. So now we can go back to the main story. We have our streaming pipeline, and we have our count operator, and now we know that this count operator is a stateful operator. So it internally keeps these counts. And what we also know is that it counts user interactions per 1 hour window. So what it does, it will ingest the data, keep updating these counts, and then after 1 hour, it will emit a result that says, in this hour, I've seen Mo 7 times, and I have seen Kafka 12 times, and so on. Now, what might be the problem with this? It's what I just mentioned, that the results only arrive by the hour. So if you want up-to-date results on how often people are mentioned or how often tweets are seen, you're out of luck right now. So the solution that we came up with for this is Queryable State, is what we're calling it. And for this, we're going to look into this operator. So this is the count operator that we are always talking about right now. And what it has internally is these states. So it knows it has seen Mo 5 times, Sue 12 times, Po 2 times. And it also has this timer service. And when the timer says an hour is up, then I basically emit my results for this hour. And with Queryable State, what we can now do is ask the operator while it is running, hey, operator, what is your current count for, say, Mo? And then the operator would give the result. The current count for Mo is 5. So what this gives the user is that it can have both these hourly results written to the Kafka log, but also it can, up to the second, know what the current count for things are. And this is actually, this Queryable State thing is driven by a project that we did together with Twitter. So you can read about it in the blog post. And they have just this case. They need to count tweets or tweet impressions and store them into some system. And they also have an API that allows users to check how often their tweets are viewed. And they had a very complicated system for this that used huge amounts of resources to do this. And with Flink, we programmed a prototype that does the same using a custom implementation of this Queryable State. And I think we did it with less than 5% of the resources. And then based on this prototype that we did, we wanted to come up with a general solution for this problem of querying the state of currently running operations. And the result is Queryable State. Now, back to our example for another interesting thing. So imagine you have this pipeline that is counting things or doing something more complex, maybe. But you have it running. And because this is a streaming program, you have it running all day, every day, 24/7, basically. And it should always keep running, because if you don't always ingest data and do decisions based on it, you might lose money, for example. So what can happen if you have this long-running job, or what are some things that might come up that you need to deal with? So say, for example, you started this program, and initially you thought, I probably have 100 tweets per day, so one machine should be fine for analyzing this data. But then you realize Twitter is somewhat successful, and there's a lot more tweets coming in. And then you might want to change this number of workers that are processing your data to fit the new characteristics of the incoming data, the throughput. So that's something that would be helpful. Then if you have your program running on one cluster, and this cluster is getting old, or some machines are failing, you might want to migrate the program to a new and better cluster. Or what you might want to do, you discovered you have some bug in your code, so you're incorrectly counting things, or your transformations are incorrect, or there might be a bug in Flink. Or you might simply want to test different versions of the algorithm on the data at the same time. And this is somewhat tricky to do, actually. But for a stateless job, this is easy. So let me explain. In a stateless job, we don't have any state in these operators. And what we can do, for example, to change the number of workers that we're running this on, is just we cancel the program, start it new on a different number of workers. And boom, done. Problem solved. It's now running on a new set of workers with more or less workers based on the throughput that we observed. But for a stateful job, this is somewhat tricky, because there are these operations running on these worker nodes that you have. But if you now want to run it on more worker nodes or less worker nodes, the state that these operations have, it needs to be distributed to these new worker nodes. So for example, if you shrink down to only one worker, all the state from these different workers needs to be put on this one worker. Or if you go from one worker to 10, the state needs to be split up and moved to these other workers. So that's quite a tricky thing to do, in fact. But the solution that we came up with for this is what we call savepoints. And what it basically allows is, so say you have your Flink job running, then at some point you decide that you want to change something or fix a code, change the number of workers on which this is running. Then you do a save point and store it to some distributed storage location. Then you change the program, and then you restart it with a potentially different amount of worker nodes or with different code. And then the program is restarted from this save point, and the state is correctly mapped to the operators, and the program can continue running with the state in place and everything continuing normally. So that's it for save points. Then there's one last interesting feature I want to mention, because I personally worked on this, is sessionization, or also called session windows. And the tricky thing here is that, for example, in a web shop, you might want to count things not per fixed time windows, so say per 10 minutes or per 1 hour, because these fixed time windows, they don't have anything to do with how the users actually behave on the website, because the user might do clicks, look at stuff, and there's this concept of one user session that you might want to analyze. And for this, you have to basically do this windowing based on the timestamps of these user events. And it turns out that this is quite tricky to do. I can't go into too many details here, but you can come to me afterwards if you're interested. But it turns out that doing sessionization based on these timestamps, if you're not sure that these timestamps are in the, or that these elements arrive in the timestamps at which they were produced, it's quite tricky. But with Flink, we have support for this out of box with the next version 1.1, which should be out in a while, maybe a few weeks. Then I finally want to mention some other cool stuff that we're working on in the community, but that I don't really have time to mention. So I mentioned that you can use these save points to change the amount of workers that are processing your job. But it might also be cool if the job would dynamically notice that there's not enough resources for processing, and then dynamically scales to more or less workers based on the demands. So that's one thing we're working on. We're also working on SQL on streams. So right now, if you want to write a streaming program, you have to be, or the engineer type, you have to write Java programs, you have to know quite a bit about some stuff. But with SQL queries, you could just write an SQL query against the stream, and then normal data analysis people or non-programmers necessarily, they could use the system to run data analysis jobs. And then there's some, that's quite low level, so we're doing some improvements to a windowing API, and for people that know Mesos, we're also working on running it on Mesos. So Mesos is basically a cluster management system that allows you to share resources between different parallel programs. And we're also working to bring support for this to Flink. That's just, if you know, there's Yarn, for example, in the Hadoop world, and there's Mesos. Right now we can run on Yarn, but we're also working on making it run on Mesos, just if you know these kinds of things. So finally, if you didn't listen to anything what I just said, I want you to get these basic things out of the talk. And if you encounter some stuff in the future, you might remember that there's some interesting stuff going on. So the basic point is stream processing is a reality now, and everyone has to do it if they want to stay in the game up to date. Flink is very good at this, and in Flink there's already quite some cool stuff, and there's more cool stuff coming up in Flink. And if you're interested in this, you can join the community or follow stuff. So there's the Apache Flink Twitter handle. There's our company Twitter handle, Data Artisans. You can read the blog of the Flink website or of the Data Artisans website. So there we are posting some interesting use cases or new developments. For example, this Twitter case that I mentioned, or some blogs together, some posts together with other companies. And of course, you can subscribe to the mailing list. So there's news, the user mailing list for user questions, and the development mailing list, where basically all the discussions about the development happen if you're interested in that kind of thing. And as a last thing, I also quickly want to mention we have our own conference, Flink Forward. It's in September in Berlin. There's already a great amount of submissions from very interesting companies in. And if you want to have a look, you can go to flink-forward.org. That's it from me. Thanks. You can now post questions if you want. I'll also be hanging outside, around outside, if you want to have a question. Yeah.
Basically, you did some stuff right from the beginning, I think, which maybe other frameworks didn't, because they started earlier. Maybe you can go into some detail what you think maybe made stuff easier for you later, and maybe other design decisions you now regret, but you can get rid of.
Yeah, that's a good question. Yeah. So there's the other big contender for streaming systems, which is Spark streaming. And I think we have the advantage over Spark streaming in that we're doing what we're calling true stream processing. So we are basically processing one element at a time as it comes in real time. And on the other end of the spectrum, there is batch processing. So for example, with Hadoop, you used to do it, so you collect your data for one day on your storage, and then you have your nightly job that analyzes this, and then you're basically 1 hour late. And what Spark streaming did is they basically reduced this wait time by a great amount, and they're calling this micro batches. So they collect data, and when they have like 1 second of data or 2 seconds of data, they process it on the Spark batch processing system and produce results. And then they wait again until the next batch is full and they process it. So this makes it very easy for Spark in some ways, because they just reuse the batch processing system to also do stream processing, but on micro batches. But for Flink, we had, through luck maybe also, but maybe also cleverness, we had from the beginning the idea that Flink should be a real streaming system that can look at elements at a time as they come in. And this allowed us to do some interesting this allows us now to do some interesting stuff that is somewhat harder to do in Spark. So I mentioned this windowing API that we have. This is very flexible, where I mentioned these sessions. So as it turns out, if you do these micro batches, and the user sessions, they don't fit into one micro batch. So say you have your micro batch every second, but a user session is longer than 1 second. Then you split this user session into, the user session is split by these micro batches. And then you have to do some clever things to fuse these sessions together again. What Flink can do is just, we see all the elements, keep some internal state about the sessions, and then when we basically have a timeout, or when there's no activity on the session for a while, then we emit the results. So this is one of the things where we're quite lucky that we made this decision, because we can now do interesting things on this. I think one regret is that, but we're working on this now, is that it's not dynamic enough. So that's an advantage of the Spark system. So because they collect these micro batches, and then basically for this schedule a batch job that processes the micro batch, they basically they schedule each individual batch individually and can choose for each batch the number of worker nodes that would process this batch, and by this they automatically get dynamic scaling, if you will, based on the incoming data. And in Flink, for a long time, things were very static. So you would start your program on a fixed number of workers, and then it would run. And you couldn't do anything about it. But now what we're doing with these save points, you can do a save point and rescale. And in the future, hopefully we'll also have truly dynamic scaling. So this is a bit of a downside of our design. But it's the only regret I can think of right now. Because the other stuff is not limited by the architecture, but just by the amount of time that we can put in. So there's all these cool new things that I'm mentioning, but right now we are low on time. So it takes some time to implement these, but in time they will all come true. Yes, please.
You mentioned that stateful, that when it's stateful, it remembers and can change state. Is that then per worker, or does it share that state across all the workers?
Yes. So the question was whether the state is per worker or across the cluster. I'm just repeating for the mic. So the state is per worker. But what we do is we have a special way of the kind of state that would be rescalable can only be used if you specify a partitioning function or a keying function of your input. So you would, for example, say that you key the data by the user ID, and then the system would route all the elements all elements with the same key to one worker, and this worker has the state for this key, and that's how this works. And if you rescale, you just make sure that the correct state for a key is on the machine where you also route the elements to after you change the parallelism. Does this answer it? Please.
Yeah, referring to what you said about micro-batching versus streaming.
Mm-hmm.
What I don't understand is that my data that's coming in, it's always quantized, at least in some form of event. So how can I avoid thinking of the data in terms of micro-batches?
So the question is, how can you avoid thinking of the data in terms of micro-batches?
So I don't see how the stream is fundamentally different from cutting up the time and looking at each time slot which contains a micro-batch.
I don't know exactly. Let me think. No, but I think there's, as I mentioned with these session windows, there's inherently the stream is not micro-batch because each element can arrive individually. But, so I don't understand what you mean exactly by micro-batches. Maybe you can further explain, then I can.
So when you do your analysis in your operator, the data is coming in.
Yes.
And that's a micro-batch.
No, but it's not. What do you mean exactly? In Flink, it's not a micro-batch. So there's basically, so the operator sits there and has the state, and then there's one event happening, for example, a tweet, and this moves through different ways into Flink and is processed as one element and not as a micro-batch.
Okay, but then I don't understand the fundamental difference between the micro-batch and the element. But maybe we can discuss now after the presentation.
Yeah, sure. Hello. Yes, please?
So the main advantage in stream processing is that you can't make the micro-batches small enough, right? So if you want sub-second latency or something like that, you can't have windows of 10 microseconds or something, but you could react to an event in 10 microseconds if you have a streaming architecture rather than micro-batches.
Yes. Yeah, so that's the extreme basically. You can have the batches like you would have in a loop, or you can make it very slow, and the extreme of it is that you have a micro-batch of size 1, which is where you look at each element separately. But yeah, Spark, for most use cases it also works. It's just if you have requirements for low latency or some other stuff regarding Windows, then it becomes a problem. But it's also good for a lot of use cases. Is there more questions? Good then. Thank you.